For centuries, we have believed in a simple truth: objects follow a single, well-defined path through space. An apple falls straight down from a tree. A car moves along a road in a predictable arc. A thrown ball traces a clean parabola before hitting the ground. This notion is not just intuitive, it's the foundation of classical physics. But what if I told you that this belief, one that has guided scientific thought for millennia, is an illusion? Imagine yourself standing at the shore of a vast ocean. A friend is drowning some distance away. Instinctively, you know that running directly toward them isn't the best choice. You'll move faster on land than in water. Instead, you adjust your trajectory, picking a path that minimizes the total time taken to reach them. This is not just a survival instinct. It's a principle deeply embedded in the very fabric of physics. But here's where things get unsettling. If we apply this idea to the way light moves, something bizarre happens. Light seems to know the best path before it even begins its journey. It bends when passing through water, precisely adjusting its course, as if it had somehow calculated the fastest route in advance. How is this possible? How does light decide where to go? Is it conscious? Is there a hidden force guiding it? Or is our understanding of motion fundamentally flawed? The classical world tells us that objects follow a single trajectory dictated by forces and momentum. But what if motion doesn't work the way we've always assumed? What if, instead of choosing one path, reality explores all possible paths at once? Hold that thought, because we are about to challenge everything you know about movement, time, and reality itself. We now face a profound question. If even something as fundamental as motion can deceive us, what else might we be misunderstanding about the universe? In the next section, we'll unravel how nature doesn't always take the shortest path, but instead, the one that obeys a much deeper law, one that hints at the hidden complexity of the quantum world. And once you see this, you'll never look at reality the same way again. But here's the strangest part: this isn't just a trick of light. It's happening to everything, all the time. Imagine you're a lifeguard at the beach. Someone is drowning, and you have mere seconds to act. Do you sprint directly toward them in a straight line? It seems like the obvious choice after all. The shortest distance between 2 points is a straight line. But if you do, you'll run fast on the sand, but move much slower once you hit the water. A better strategy is to adjust your path, running at an angle, so you enter the water at a point that minimizes the total time taken. Without even realizing it, you've just applied a fundamental principle of physics, one that governs not only human decisions, but the way light itself moves through the universe. This principle is known as the principle of least time, also called Fermat's principle. It states that light does not simply travel in a straight line. Instead, it takes the path that requires the least amount of time, even if that means bending through different mediums. When light moves from air into water, it slows down. To compensate for this, it bends at just the right angle, so as that its total journey, air plus water, takes the shortest possible time. But here's the unsettling part: how does light know to take the optimal path before it even starts moving? This question has puzzled scientists for centuries. Does light possess some kind of foresight? Does it test all possible paths before choosing the best one? Or is there a hidden, underlying rule that determines its movement? This strange behavior isn't just limited to light, it applies to all motion in the universe. From the flight of planets to the way electrons move inside atoms, everything follows a deeper rule, one that does not always obey our common sense about the shortest path. Classical physics tries to explain motion using forces. If you push an object, it moves in the direction of the force. If no force acts on it, it keeps moving in a straight line. Simple, right? But nature is far more sophisticated. Instead of calculating forces, the universe seems to operate by choosing paths based on a hidden quantity called action. Action is a mathematical concept that, for centuries, seemed like an abstract curiosity, but as we'll soon see, it's the key to unlocking the bizarre world of quantum mechanics. To make things even stranger, light doesn't just choose a path based on local conditions. It somehow knows the entire situation before making its move. This behavior becomes even more perplexing when we shift from classical physics to quantum mechanics, where particles behave as waves and seem to explore multiple paths simultaneously. So far, we've seen that light, and by extension, reality itself, does not always take the shortest path, but rather the one that obeys a deeper principle. But if light can bend its trajectory in this way, what happens when we look at the motion of subatomic particles, electrons, and even entire objects? As it turns out, motion at the quantum level does not just follow a single well-defined path. Instead, it follows all possible paths at once. This idea is not science fiction, it's at the core of modern physics. And in the next section, we'll uncover the mind-bending realization that motion itself is not what we think it is. Get ready, because we're about to shatter the illusion of a single reality. For centuries, we believed that light traveled in a straight line, obeying simple, predictable rules. But as we've just seen, light seems to know the fastest path before it even begins its journey. This alone is strange enough, but what if I told you that light isn't actually choosing just one path at all? Instead, it explores every possible path simultaneously. This idea was first hinted at when scientists began studying how light behaves under extreme conditions. When passing through a prism, it splits into a rainbow of colors, each bending at a slightly different angle. But what happens when light encounters a barrier with two slits? Instead of forming two distinct beams, an interference pattern emerges, as if each individual photon had somehow traveled through both slits at the same time. This effect, known as the double-slit experiment, shattered everything we thought we knew about motion and reality itself. How can a single particle of light go through two paths at once? Classical physics had no answer. This discovery forced scientists to reconsider not just the nature of light, but the very fabric of reality. What if motion itself is an illusion? What if light and all matter does not take a single path, but instead all possible paths simultaneously? To truly grasp this, we need to introduce a concept that has remained hidden in physics for centuries: action. Action is not a force, nor is it energy, it's something deeper. It is the hidden quantity that determines how objects move through space and time. While classical mechanics relies on Newton's equations of motion, modern physics reveals that the universe doesn't calculate motion by force, but by action. Action works in a strange way. Imagine throwing a ball. In the classical world, we say that gravity pulls it down along a single trajectory, but in reality, the ball explores every possible trajectory at once. Some of these trajectories interfere with each other and cancel out, while others reinforce one another. The path we actually observe is simply the result of this deeper process of interference. This same principle applies to light. Light explores all possible paths between 2 points, and the paths that agree with each other reinforce, creating the familiar straight line motion we see. But at the microscopic level, the interference pattern of paths becomes visible, revealing the hidden complexity beneath what we assume to be reality. This realization set the stage for a revolution in physics. If light and, by extension, all particles can explore multiple paths, then reality itself must be far stranger than we ever imagined. This insight was the key that unlocked the door to quantum mechanics. In the next section, we'll uncover how Max Planck's groundbreaking discovery stood the very foundations of classical physics and led us into the era of quantum mechanics. A discovery so unsettling that even Planck himself didn't fully understand its implications. At the dawn of the 20th century, physics stood on a pedestal of certainty. Scientists believed they had decoded the fundamental rules of the universe. Newton's laws, electromagnetism, and thermodynamics seemed to explain everything. But then, a peculiar mystery arose, one that refused to fit within the existing framework of physics. It was called the ultraviolet catastrophe. This was no minor problem, it was a crisis, When scientists tried to apply classical physics to predict the energy emitted by hot objects, the math collapsed. The equations suggested that an object should release infinite energy at high frequencies, an absurd result. Something was missing, something fundamental. It was Max Planck who stumbled upon the answer. In an act of sheer desperation, he proposed something radical. Energy is not continuous, but quantized. Instead of being emitted in smooth, infinite waves, energy came in tiny, indivisible packets, what we now call quanta. This single assumption fixed the equations, resolving the ultraviolet catastrophe. But at the time, Planck himself did not grasp the full magnitude of what he had just discovered. In fact, he resisted the idea. He had no intention of overthrowing classical physics, yet that is precisely what he had done. While Planck's idea was meant to be a simple fix, Albert Einstein saw something deeper. He realized that if energy itself came in discrete packets, then light itself must be made of particles. This was unthinkable. Light was supposed to be a wave. But Einstein's interpretation explained something else that had baffled physicists for years: the photoelectric effect. Scientists had observed that shining light on a metal surface could knock electrons loose, but only if the light was above a certain frequency. According to classical physics, increasing the brightness of light should provide more energy to dislodge electrons, regardless of frequency. But that's not what happened. Instead, Einstein's bold idea explained that light was composed of individual particles, later called photons, and each photon carried a precise amount of energy. If the photon's energy wasn't high enough, no electron would be ejected, no matter how much light was present. This was the moment physics split in two. On one side, light behaved like a wave, creating interference patterns. On the other, light behaved like a particle, with distinct energy quanta. The contradiction was maddening. How could light be both a wave and a particle? What Einstein had uncovered was only the beginning. His discovery didn't just apply to light, it hinted at something far greater. If light could behave as both a wave and a particle, what about matter? Could electrons, atoms, and even entire objects also have wave-like properties? This question would soon lead to an even deeper mystery, one that would shake the very foundation of reality, and the answer would come from an unexpected place: a young physicist named Louis de Broglie, who would propose an idea so radical that it would change physics forever. With Einstein's groundbreaking discovery that light behaves as both a particle and a wave, physics found itself in a paradox. The classical world had collapsed, and what stood in its place was something far more bizarre. But Einstein's revelations were just the beginning, because what followed next was a battle of ideas that would shape the future of science. At the center of it stood two of the greatest minds of the 20th century, Albert Einstein and Niels Bohr. Bohr took Einstein's quantum light theory and pushed it even further. If light, something long believed to be purely a wave, could also behave as a particle, what about electrons, atoms, entire systems? What if, instead of following clear, predictable orbits around the nucleus, electrons moved in quantized jumps, existing in multiple states at once until measured? Bohr proposed a radical solution, the Copenhagen interpretation. He argued that particles don't have a definite state until observed. Instead, they exist in a superposition of possibilities, collapsing into a single reality only when measured. This idea flew in the face of everything Einstein believed about physics. To Einstein, nature had to be objective, real, independent of whether someone was observing it or not. And so, a legendary debate was born. Einstein could not accept that reality depended on measurement. He famously said, "God does not play dice with the universe." He was convinced that quantum mechanics was incomplete, that there had to be hidden variables determining a particle's state before observation. To him, Bohr's vision of reality was an unsettling departure from everything science had achieved. Bohr, however, had an answer to Einstein's skepticism. He argued that quantum mechanics doesn't describe what reality is, but only what we can know about it. This was an entirely new way of thinking about physics. Instead of definite positions and paths, everything was governed by probabilities. To prove his point, Bohr pointed to a peculiar phenomenon already observed in experiments: wave-particle duality. When electrons were fired one by one at a double slit, they didn't behave like tiny billiard balls. Instead, they interfered with themselves, as if they had traveled through both slits at once. Yet, when measured, they suddenly chose a definite path. This wasn't just a strange property of electrons, it was a fundamental feature of reality. This was no longer a battle over abstract theory. If Bohr was right, then reality itself was not made of definite things, but of probabilities and possibilities. And if electrons could act like waves, then what about larger particles? What about entire atoms? What about us? Enter Louis de Broglie, who took this idea to its extreme. If light and electrons could behave as both particles and waves, why wouldn't all matter behave this way? His answer was as simple: it was shocking. Everything in the universe, including you, has a wavelength. In the next section, we'll explore this mind-blowing idea. If everything is a wave, what does that mean for the way we experience reality? Imagine looking in the mirror and realizing that you are not just a collection of particles, but also a wave. This is not a metaphor, it is a fundamental truth of reality. After Einstein and Bohr's debate on the nature of quantum mechanics, one physicist took the idea to its most extreme and profound conclusion. His name was Louis de Broglie, and his discovery shattered our very concept of existence. If light could behave as both a wave and a particle, de Broglie asked, why should electrons be any different? And if electrons were waves, what about atoms, molecules? What about something as large as a human being? He proposed something so radical that even seasoned physicists struggled to accept it. Everything has a wavelength, including you. At first, this sounded like pure speculation, but then came the proof. Scientists soon devised experiments that showed electrons, tiny bits of matter, could create interference patterns, just like light waves. This meant electrons were not simply particles, but wave-like entities, existing in a spread-out form until measured. De Broglie had uncovered something extraordinary. All matter moves through reality as a wave, only appearing solid when observed. De Broglie's idea wasn't just a theory, it was a fundamental principle of nature. He demonstrated that the motion of any object determines its wave-like nature. In simple terms, the more momentum an object has, the smaller its wavelength becomes. This means that while large objects like a baseball or a human seem solid and well-defined, as a microscopic scale, particles like electrons and protons behave more like waves. To visualize this, imagine ripples forming on a pond. When the ripples are large, they are easily noticeable, much like the wave-like nature of tiny particles. But as the ripples become smaller, they fade into what looks like still water. Just as larger objects appear solid to us, even though at a deeper level, they too have wave-like properties. To truly grasp the significance of this, let's return to the double-slit experiment. Previously, we saw that light could interfere with itself, proving its wave nature. But when the experiment was conducted with electrons, particles of matter, the results were the same. Electrons, when unobserved, formed an interference pattern, but the moment they were measured, they collapsed into single, defined points. This means that an electron does not take a single path from point A to point B. It takes all possible paths at once until someone looks. And if electrons behave this way, then so do atoms, molecules, and potentially us. This discovery didn't just change physics, it changed our understanding of existence itself. If all matter is also a wave, then everything we perceive as solid is merely a manifestation of quantum interference. The question is no longer whether quantum mechanics applies to us, it's how far this strange reality extends. In the next section, We'll revisit the double-slit experiment in more detail, because if everything follows quantum rules, then reality itself is not what it seems. What does it mean to be real when matter can exist in multiple states at once? Get ready, because we're about to confront the most unsettling proof in all of physics. If you had to choose one experiment that completely rewrote our understanding of reality, it would be the double-slit experiment. It is simple in design yet devastating in its implications. It doesn't just reveal the strange behavior of quantum particles, it forces us to question the very nature of existence itself. Imagine you have a wall with two small slits. Behind the wall is a screen that will detect whatever passes through the slits. Now, you begin by firing tiny particles, like grains of sand, at the slits. As expected, they either go through the left slit or the right slit, forming two distinct patterns on the screen. But what happens if, instead of grains of sand, we fire electrons, tiny subatomic particles? Logic tells us they should behave the same way, forming two distinct bands. Instead, something impossible happens. The electrons do not form two bands. Instead, they create an interference pattern, as if each electron had somehow traveled through both slits at the same time, interfering with itself like a wave. This alone is mind-boggling, but the real mystery is what happens next. Scientists then placed a detector at each slit to observe which path the electron actually took. And the moment they did this, the interference pattern disappeared. Instead, the electrons behaved like particles again, forming two distinct bands just like the grains of sand. In other words, the mere act of measuring which slit the electron passed through changed its behavior. When not observed, it behaved like a wave, exploring all possible paths simultaneously. But the instant it was measured, it chose a definite trajectory and acted like a particle. This is known as the observer effect, and it's one of the greatest mysteries in physics. What does it mean for reality if a quantum system only decides on an outcome when it is observed? Does this suggest that consciousness itself plays a role in shaping the physical world? Or is there an even deeper principle at work, one that we have yet to understand? The double-slit experiment shows us that matter does not behave in a definite way until it is observed. This completely contradicts our everyday experience, where objects have a clear position and path, independent of whether we are looking at them. But at the quantum level, reality is not fixed. It is a sea of possibilities that only solidifies when measured. This leads to unsettling questions. If electrons, and by extension, all matter, behave this way, what does it mean for the nature of reality itself? Are we living in a world that only exists when observed? Could the universe itself be participatory, requiring consciousness to become real? Some physicists believe this experiment is the clearest evidence that reality is not objective in the way we assume. Others argue that measurement does not require consciousness, but rather interaction with any macroscopic system. Yet, the deeper mystery remains: what exactly collapses the wave function, forcing matter to take on a definite form? If the double-slit experiment proves that particles explore multiple paths before choosing one, then what if this is happening all the time, everywhere, with everything? Richard Feynman took this idea to its logical extreme. He proposed that every particle in the universe explores all possible paths simultaneously, only appearing to follow a single trajectory due to interference. In the next section, we will dive into the Feynman path integral, a theory that suggests that every moment of existence is a sum of infinite possibilities. What if reality is not a straight path, but a web of endless trajectories, all happening at once? Imagine dropping a ball and watching it fall to the ground. It seems to follow a single, predictable trajectory. But what if I told you that, in reality, that ball didn't just fall in one path, but in every possible path simultaneously? This isn't science fiction. This is the profound realization of Richard Feynman's path integral formulation of quantum mechanics, one of the most astonishing ideas ever proposed in physics. Feynman suggested that particles do not take just one path From point A to point B, they take every conceivable path. Some of these paths seem completely absurd, curving wildly before reaching their destination. Others follow nearly straight lines. The reason we observe only one trajectory in the macroscopic world is because most paths cancel each other out due to quantum interference, leaving behind only the most probable one. But at the quantum level, this cancellation does not happen in the same way, allowing multiple paths to remain relevant. This means that when an electron moves from one place to another, it doesn't just travel in a straight line, it explores every possible route, including those looping through space and time in ways that defy intuition. Reality, as we experience it, is just the result of an infinite number of these paths interfering with one another. At first, this idea seems impossible. If particles take all possible paths, why do we only see them following one trajectory? The answer lies in the principle of least action, a hidden rule governing all of physics. Imagine a pond with ripples spreading out in all directions. Most waves cancel each other out due to destructive interference, leaving behind only the strongest patterns. The same thing happens with particles. The vast majority of paths interfere destructively and vanish, while only a narrow range of paths reinforce each other. This results in what appears to be a single, well-defined trajectory, but in reality, it's the outcome of countless possibilities interacting beneath the surface of reality. The implications of this are staggering. If every particle follows all possible paths, then the entire universe is operating on this principle. Every moment, every event, every choice is a sum of infinite possibilities. But this leads us to a deeper question: if reality is the result of all possibilities, does this mean the future is also undetermined until observed? Feynman's idea doesn't just apply to small particles, it extends to everything. The way we observe motion, the passage of time, even the fabric of space itself, is governed by the path integral. This means that the past, present, and future are not fixed. Every possibility exists until it is observed. This ties directly into the concept of quantum superposition, where particles do not exist in a single state until measured. If everything follows Feynman's path integral, then we are constantly collapsing infinite realities into one perceived reality, moment by moment. This brings us back to the biggest question of all: if the universe explores all possible outcomes, what does that mean for free will? Is every decision we make just a collapse of infinite paths into one perceived choice? Or do all choices exist simultaneously, only appearing singular because of quantum interference? We've now uncovered a universe far stranger than we ever imagined, one where every possible trajectory exists, yet we only perceive one. But this raises a final mystery: if all paths exist, why does nature seem to select the best one? Why do objects move in predictable ways, despite infinite possibilities? In the next section, we will explore the principle of least action, the hidden law that determines why reality unfolds the way it does. If we can understand this principle, we might finally grasp the true mechanics behind existence itself. We've uncovered a universe where particles take all possible paths, where reality is a sum of infinite possibilities. But if that's true, why do we only see one outcome? Why do objects seem to move along predictable paths instead of chaos? The answer lies in one of the most profound principles in physics, the principle of least action. At first, this principle sounds almost mystical. It states that nature always chooses the path that requires the least amount of action. But what exactly is action? In physics, action is a hidden quantity that determines how motion unfolds. Instead of objects blindly obeying forces, like in Newtonian mechanics, modern physics suggests that objects follow a trajectory that minimizes action, almost as if nature itself is calculating the best route. Imagine a river flowing down a mountain. Water does not randomly carve its path. It always follows the path of least resistance. Similarly, particles do not randomly choose their trajectories. They follow the path that minimizes action. This is why light bends in a specific way when passing through glass or water, It follows the fastest route, not necessarily the shortest one. And this isn't just a trick of light. This law governs all motion in the universe. This principle is more than just an observation. It is a fundamental law of physics, deeply embedded in the equations of motion. The Lagrangian and Hamiltonian, the core tools of modern physics, are based entirely on this concept. These mathematical formulations describe everything, from the orbits of planets to the behavior of subatomic particles. Physicists describe action as the integral of the Lagrangian over time. But instead of drowning in equations, let's consider a simple analogy. Imagine trying to walk across a busy city. You could take countless possible routes, but your brain naturally finds the most efficient path, one that avoids unnecessary detours, while still reaching the destination quickly. In a way, the universe does the same thing. Out of all possible paths, only those that follow the principle of least action survive. This is why, despite Feynman's idea that particles take all paths, we perceive only one outcome, because in the end, the paths that interfere constructively are the ones that align with the principle of least action. All other possibilities cancel out. This principle isn't just a quirk of subatomic physics, it governs everything. The way planets orbit stars, the way rivers carve valleys, even the way you move when walking or running, all of it follows the principle of least action. This idea doesn't just describe motion, it describes the evolution of the universe itself. If we zoom out, we realize that the principle of least action is at the heart of Einstein's general relativity, where space-time bends to create the most efficient paths for objects in motion. It is also embedded in quantum mechanics, where wave functions evolve according to this very principle. Whether we look at the smallest particles or the largest galaxies, the universe operates with an almost eerie efficiency, selecting the most natural paths to unfold reality. So far, everything we've explored has been deeply theoretical, but how do we know this principle is real? The answer lies in experiments that reveal its eerie precision, proof that nature truly does calculate the best possible path. In the next section, we'll examine the diffraction grating experiment, one of the most compelling demonstrations that the principle of least action isn't just an abstract idea, it's an undeniable part of reality itself. We've explored the theoretical foundation of the universe, how reality selects the most efficient path through the principle of least action. But theory alone is not enough. How do we know that these ideas aren't just elegant mathematics, but the actual governing laws of nature? The answer lies in one of the most astonishing experiments ever devised, the diffraction grating experiment. This test not only confirms that light and all matter obeys the principles we've discussed, but it does so with eerie precision. Imagine shining a beam of light through a finely spaced set of slits. This is called a diffraction grating. Classical physics would predict that light should simply pass through and create an evenly lit area on the other side. But what actually happens is far stranger. The light spreads out and forms an intricate interference pattern, with alternating bright and dark bands. This pattern is undeniable proof that light is exploring multiple paths simultaneously and interfering with itself. This experiment doesn't just work for light. It has been repeated with electrons, atoms, and even entire molecules. No matter what we send through the grating, the result is the same, an unmistakable interference pattern emerges. This confirms what Feynman, de Broglie, and countless others proposed, that everything follows all possible paths, and what we see is just the result of quantum interference. But what does this have to do with the principle of least action? The answer is stunning. If light were to take just one path, as classical physics once suggested, we wouldn't see any interference at all. Instead, the bright and dark bands prove that light, and by extension, all matter, follows every possible route, but only certain paths reinforce one another to create a visible pattern. This is the direct, experimental confirmation that the universe truly does choose the most optimal paths through a process of interference and cancellation. What we perceive as solid, predictable motion is actually the result of deeper, hidden laws operating beneath the surface of reality. Even more astonishing is the precision of this phenomenon. The interference pattern isn't random, it appears with mathematical exactness, showing that quantum laws are not chaotic, but beautifully structured. This suggests that the fabric of the universe itself operates under principles of optimization, as if fine-tuned by some deeper logic. The diffraction grating experiment forces us to confront some of the most profound questions in science. If the universe operates under such optimized laws, does this imply that reality itself is constructed in a way that ensures efficiency and order? Could this be a sign that our universe isn't just randomly unfolding, but is instead governed by rules that maximize stability and coherence? This raises an unsettling possibility. If everything follows the principle of least action, does this mean our own decisions, thoughts, and actions are also the result of optimization? Could the choices we make be predetermined by the same fundamental laws that shape the cosmos? Some physicists argue that this is evidence of a deeper intelligence embedded within the structure of reality, and necessarily in a supernatural sense, but as an inherent property of the universe itself. Others believe this is simply the inevitable outcome of mathematics in action. Either way, the experimental proof is undeniable. The universe does not waste effort, and everything follows a hidden order far beyond what we can see. Now that we have experimental confirmation of these profound ideas, the next step is to ask, what else is hidden in the fabric of reality? Scientists are now searching for a single equation that can unify all the forces of nature, a formula that could explain everything, from the smallest quantum interactions to the vast structure of the cosmos. In the next section, we will explore this quest for the theory of everything, a journey that may reveal the deepest secrets of the universe itself. Could we be on the verge of unlocking the ultimate law of existence? We've uncovered some of the deepest truths about reality, from the strange paths of quantum particles to the elegant principle of least action that shapes the universe. But despite these breakthroughs, one question remains unanswered: what is the ultimate equation that explains everything? For centuries, physicists have sought a single, unifying theory that could describe all forces of nature in one elegant framework. Einstein spent the last years of his life chasing this dream, trying to merge general relativity, which governs gravity, and the cosmos with quantum mechanics, which dictates the behavior of subatomic particles. But even Einstein couldn't solve this final puzzle. Today, scientists continue this quest, searching for what they call the theory of everything. If such an equation exists, it would not only explain why reality is structured the way it is, but could also reveal the deepest, most hidden truths about existence itself. Could this equation already be within our grasp? The biggest challenge in finding the theory of everything comes from the fundamental clash between two of the most successful theories in history. General relativity describes gravity as the curvature of spacetime, working flawlessly for massive objects like planets, stars, and galaxies. Quantum mechanics governs the behavior of the tiniest particles, predicting uncertainty, probability, and wave-like behaviors that defy intuition. Each theory works perfectly in its own domain, but when we try to merge them, everything collapses. The equations break down, giving infinities and contradictions, especially in extreme environments like black holes or the beginning of the universe. It's as if we are missing a deeper layer of reality that unites both perspectives. To bridge this gap, physicists have proposed several radical ideas. String theory. Instead of treating particles as tiny points, string theory suggests they are vibrating strings in a multidimensional space. Different vibration modes correspond to different particles, and gravity emerges naturally from the framework. The problem? It requires extra dimensions, possibly 10 or more, that we cannot yet observe directly. Loop quantum gravity. Instead of modifying particles, this theory suggests that space itself is quantized. Just as energy comes in discrete packets quanta, spacetime might also be composed of tiny, indivisible units. If true, this could solve the puzzle of merging gravity with quantum mechanics. Emergent spacetime, some scientists suggest, that space and time are not fundamental at all, but instead emerge from deeper quantum processes. This would mean that the universe itself is an illusion built from a deeper, hidden layer of physics. Each of these ideas could be the key to the ultimate equation of the universe. But so far, none of them have been fully proven. What happens if we find the final equation? If physicists discover the theory of everything, it could unlock unimaginable possibilities. We might finally understand what happened before the Big Bang, whether parallel universes exist, and whether reality itself is deterministic or shaped by probabilities. More than that, it could lead to advancements in technology, space travel, and even consciousness itself. But here's the paradox: if we find the equation that explains everything, does that mean we've reached the limit of human knowledge? Or could it reveal even deeper mysteries beyond our comprehension? Some scientists believe that every time we think we've found the fundamental truth, we only uncover another layer of reality hidden beneath it. Could the search for the ultimate equation be an endless journey, revealing deeper and deeper truths for eternity? So, after all this, we are left with a final question: is reality governed by a single, elegant equation? Or is the universe far stranger and more complex than we could ever imagine? Perhaps the greatest mystery of all is that the deeper we look into the cosmos, the more it seems that the universe is not just a machine, but something much more profound and endless, unfolding mystery that may never truly be solved. What do you think? Could we one day unlock the final equation of existence? Or will the universe always hold secrets just beyond our reach?